Today we talked about the limit definition of a derivative, which is the limit as h approaches 0 of f of x plus h minus f of x divided by h. And what this is this is the average rate of change formula in disguise. So if we look at this f of x plus h minus f of x, we can treat that as y2 minus y1, and then h, which is really just x plus h minus x, that simplifies to h. This is x2, bad bracket, x2 minus x1. So really we have 2 points here. We have the point that happens at x comma f of x, and then we have the point that happens at x plus h comma f of x plus h. So what we're saying is, if we plug in x to the function, if we plug in x to the function, we get an output of f of x. If we change x a little bit, like we add some number h to it, well, that's going to change the output too. So what we're doing is we're taking a limit as h approaches 0, because what we want to do is we want to make these 2 points become increasingly close together. So it helps if we look at an example. Here we have the function f of x equals x squared. So what we have is we have f of x plus h, which is just f of x with x plus h plugged in. So we have x plus h squared minus f of x divided by that h. And we're going to take a limit as h approaches 0. So how we can actually simplify this limit is to FOIL out x plus h squared. So we now have the limit as h approaches 0 of x squared plus 2xh if we FOIL plus h squared minus x squared still divided by h. Okay, and then that's going to simplify as the limit still as h approaches 0. Okay, so let's see what we got. We have an x squared and a negative x squared. Okay, so this is 2xh plus h squared divided by h. Okay, so what I'm going to do is I'm going to factor out an h, because they both have an h, so let's do that now. Okay, so then what we can do is once we factor out that h, we have h times 2x plus h. So because we're multiplying, we can cancel these h's, and we're left with 2x plus h. So now if we were to plug in h equals 0, which is our limit, now we don't have an issue anymore. Before, if we plugged in h equals 0 right here, we get x squared minus x squared, which is just 0 over 0, and 0 over 0 is an undefined value. But now that we've canceled this h, we can just plug that 0 right in, and we get just 2x. Okay, 2x, which is our derivative of x squared. So what we should do now is look at the graphical representation of the limit definition. So here what we have is I sketched x squared, and we have some random point x. When we plug in x, we're going to get f of x, which again is just going to be x squared. And then here's x plus h. It's x with a little bit of a difference, right? So the difference between them is h. And when we change x by that amount, when we add h to it, well, we plug that into the function and we get a different output. It's f of x plus h. So now we have 2 points. And if we want to find the average rate of change between those 2 points, we can just draw a line between them. We call this a secant line. So then if we take a limit as h approaches 0, what's going to happen is, okay, well, this is h, right? So if h is going to 0, then these two x values are going to become increasingly close together. And when that happens, these points are going to become increasingly close together. We're still taking an average rate of change between them, but if you take an average rate of change between 2 points that are basically right on top of each other, right next to each other, you end up with a tangent line, which is what our derivative is. It tells us the slope of that tangent line at any given point. So here I've drawn 2 points that are really close together. I've drawn an average rate of change line between them, but because they're so close together, that's starting to look like a tangent line. And as h goes to 0, when h becomes 0, they're going to be right on top of each other, and that's going to give us the exact derivative. So that's how our limit definition functions. And without this definition, we wouldn't be able to find the slope of any function at any given point. It requires us using limits. But once we understand this definition, we can start to look for patterns, which is where the power rule comes into play. So just give me a second here. I'm going to lay 3 different examples out right on top of each other, and we can examine how the power rule works. Okay, so here we have 3 different examples. We have the function x squared, the function x cubed, and the function x to the 4th. And when we expand out x plus h squared versus x plus h cubed versus x plus h to the 4th, we have to use something called the binomial theorem or Pascal's triangle. And we are not super concerned with you knowing the Pascal's triangle or being able to expand this, but this specific example will help us understand the power rule. So just using Pascal's triangle, look it up if you want, we're able to expand x plus h cubed as this, and x plus h to the 4th. Sorry, it cut off for a second there because my iPad's dying. I said x plus h to the 4th expands as this. Now, if we look at these, well, we know that the x squared will cancel with the negative x squared, and the x cubed cancels with the negative x cubed, and the x to the 4th cancels with the negative x to the 4th. And then we look and we say, well, if we factor out an h, there's going to be an h left over here, which goes away because h is approaching 0. And then this h cancels with this h, and we're left with our derivative of 2x. So coming down here to the x cubed example, well, we factor out an h. We're left with h squared here, which is going to go away because h is approaching 0. We're left with an h here, which is going to take this whole term away. But then when we factor out this h, that cancels with the denominator h, and we're just left with 3x squared. And then popping down to the last example, okay, we factor out an h. We're left with h cubed right here, which is just going to go away because h is approaching 0. H squared is going to be left here, but that's going to go away too because we're going to multiply the whole thing by 0, which is going to cancel it, right? Here we're left with an h again, so h is 0, so that whole thing goes away. This h cancels with this h, and we're just left with 4x cubed. So what do we notice? Well, the derivative of x squared is 2x. The derivative of x cubed is 3x squared. The derivative of x to the 4th is 4x cubed. So what we see is, well, it seems like we're multiplying the, when we find the derivative, we're multiplying by the exponent, right? And then we're subtracting 1 from the exponent. So x to the 4th, when we find the derivative, well, there's our exponent 4x, and then we subtract 1 from 4 to get cubed. So it's 4x cubed. And that's exactly what the power rule says. To find the derivative of a function, you can take each term, multiply the coefficient by the exponent, and then subtract 1 from the exponent. So let's look at some more complicated examples. Here we go. So we have these two functions, square root x and 6 over x to the 4th. I've rewritten them as x to the 1/2 and 6 times x to the negative 4 respectively. Remember, when you have a variable in the denominator with some exponent, you can make that exponent negative and move it to the numerator. So let's apply our power rule. We have x to the 1/2, so we're going to do 1/2 out front. X, and then what's 1/2 minus 1? Well, it's 1/2 minus 2 over 2, which is negative 1/2. So our new exponent is negative 1/2. So then again, with that negative exponent, we can drop that to the denominator. We get 1 over 2 times x to the 1/2, which simplifies to 1 over 2 root x. One of those derivatives you should probably just memorize, but here we have all the work laid out for how to show that derivative using the power rule. Now for the next one, we're going to multiply 6 by negative 4 and get negative 24. X to the what's negative 4 minus 1. It's helpful to write this out so we don't mess up. Negative 4 minus 1 is negative 5, so we have x to the negative 5. And our final answer is negative 24 over x to the 5th. So with our new power rule, we can now describe the slope of a lot of different functions so long as we can find the derivative using the power rule. So these functions will tell us the derivative or the slope of the tangent line at any given x value of these functions that we're working with, and we can do that with a lot of functions now.